Hello, and thank you for joining us. Today's webinar topic is Less is More, Developing Green Methods to Increase Throughput for the M-7600. Our presenter today is Sarah Kennedy, Applications Chemist for Teledyne Leeman Labs. If you have any questions, please feel free to submit the questions throughout the presentation or email Sarah directly, and she will follow up with you after the webinar concludes. This webinar is being recorded and will be available within a few days. And now I'm going to turn it over to our presenter, Sarah Kennedy.
Thank you, Shelley. First, I want to thank you all for joining me today. My name is Sarah Kennedy, and I'm the Applications Chemist here at Teledyne Leeman Labs. Today, I will show you how to develop methods for higher throughput using our green chemistry tubing. So I will start by providing some background on our green chemistry tubing configuration, what it is, and what benefits it provides. Then I will demonstrate how methods can be developed in real time using the Quick Trace software. And I'll conclude by showing you a super fast method that I developed for US EPA 245.1, which is mercury in water by cold vapor atomic absorption, which uses the green chemistry tubing harness to get results in 70 seconds per sample. So green methods can save you time and money when they're optimized for speed. As Shelley mentioned, be sure to submit any questions you have as we go along, and I'll be able to answer those once the presentation has concluded. So let's get started. So why create a green chemistry option? Teledyne Leeman Labs set out to use the principles of green chemistry to reduce the environmental impacts of our best-selling system, which is the Quick Trace M-7600 cold vapor atomic absorption mercury analyzer. We realized this would not only reduce the operational costs for our customers, but would also benefit the environment by reducing the waste generated by daily use. So with instruments all over the world, creating an alternate green chemistry pump tubing configuration would allow us to support current and future customers' climate-conscious initiatives while creating a more sustainable future for this product line as well. So our big three questions for this project were, can we support the green goals of our customers by reducing the environmental impact of the Quick Trace M-7600? Does this change produce results comparable to the current instrument performance specifications? And can we make this modification simple for the customers to implement? And the answer to all those questions is yes. Our aim was to make the transition seamless while creating a tubing harness with a smaller internal diameter to reduce the uptake, and it still needed to meet our current instrument performance criteria. So to accomplish our goal, we experimented with various configurations and trials that ultimately maintain the same reagent to sample ratio while reducing the inner diameter of the tubing set. So we chose a peristaltic pump harness that is identical to the standard setup, except we're swapping in a smaller internal diameter tubing to reduce waste generation. So in channels 1 and 2, which are the drain lines, and channel 3, which is the sample uptake, we use a white tubing, which is part number 15-4308-102. So the first three channels are all identical. And then in channel 4, we use the orange-yellow tubing, which is part number 15-4309-102. And we kept the T connections the same just to keep everything simple. The only thing we changed were the tubing themselves. And so when you convert to the new tubing, you'll need to adjust the tension on the levers. So this process is best described in the user's manual for the instrument. I'm also putting together a YouTube video for this procedure, so keep an eye out for that. But basically, you'll want to twist the screws so there's no tension on the tubing, then slowly increase the tension by turning the knobs. And once you get a jerky back and forth motion through the transfer lines, then you'll do one full 360 turn and lock it down, and that should be just about perfect. So again, consult your manual for that, and remember to set it and forget it. Always change the tubes and not the tension when it's time for maintenance. So this graph compares the flow rate at 100% pump speed for both tubing configurations. So the green tubing setup is kind of glowing green on the bars. So for the green chemistry tubing, the stannous chloride reagent flow is 2.7 milliliters per minute, which is about 47% of the standard tubing flow. And the sample flow is 10.1 milliliters per minute, or about 67% of the standard tubing flow. So you can see that while the flows were reduced overall, they maintained a similar ratio between the tubing sets. So using the green chemistry pump tubing configuration means less is more. By reducing the internal diameter, and therefore the flow, stannous chloride consumption is reduced by 53%, sample and rinse uptake is reduced by 33%, and waste generation is down 40%. And because your sample uptake is less, this might allow you to scale down your sample prep procedure. And you can also reduce the amount of time per sample required for analysis with some method optimization. And all of that leads to more. The less time per sample means more samples per hour. You get the benefit of cost savings on prep chemicals like stannous chloride and waste disposal costs as well. So I did some math based on the price of a 500-gram bottle of stannous chloride dihydrate crystals. So for me, it ends up being about $100 per liter of 10% stannous chloride solution. So by switching to the green chemistry tubing harness, the stannous chloride reagent costs were reduced by about $150 if I ran for an entire 8-hour day. And if I ran 8 hours a day for 260 days a year, that would add up to a savings of almost $39,000. So it adds up. And also, when purchasing a 12-pack of the new green chemistry tubing, the part numbers that I read off a couple slides ago, it only costs about $3.40 more than for the 12-pack of the standard tubing. So the cost is far outweighed by the savings. So switching to the green chemistry tubing harness is a worthwhile investment for all M-7600 users. So now that we've gone over what the green chemistry tubing configuration is and the benefits it can provide, let's move on to how methods can be developed in real time using the QuickTrace software. So first, I'll give an overview of the method editor in the software, and then I'll compare peak profiles using the standard tubing and the green tubing. And you can see how much faster the analysis times can be with a little optimization. So to open the method editor in the software, we'll click on this icon. It looks like a little check sheet with a flask, and that will pull up this software here. So within the method editor, we have File, where you can save, print, or exit. Next, we have Tools, where you can add units, and you can also change standard IDs. And we also have the Help menu. Under the Conditions tab, there are two sub-tabs, the Auto Sampler and the Analyzer. Under the Auto Sampler, we can change the probe depth, the Auto Sampler rinse pump speed, sample uptake time, and rinse time. Under the Analyzer parameters, we have the gas flow rate and also the pump speed. Then we have our baselines and integration times. So these are color-coded to the chart on the right. So the first baseline is this teal maroon, and the peak integration is the red-green. Their default is 40 to 44 seconds, and this default's at 68 seconds. And if you want to add in your second baseline correction, it's green and purple. So let's type that in and move it over. Like that. So you can type in the box to change the value. You can also use the arrows to click up and down. And you can also use the interactive graph to grab the entire line and scoot it back and forth. So multiple ways to get the same outcome. You can also choose to exclude the 2 point. If you don't want the second baseline on the end, you don't have to include it. So for the chart controls, we have toggle the lines, which makes more sense when you have a graph there. Copy the chart to the clipboard. You can print the graph, unzoom. So you can click and drag to create a box and zoom in. You can also zoom out using that same button. And then if you hold in your right mouse button, you can move the graph back and forth. So unzoom kind of resets to the default. Analyze a single sample. So this is the peak profile that I'm going to talk about today. This is our primary tool for method development. So it's called Analyze Single Sample. We have the stop button. It's grayed out right now since we aren't running any samples. Then we have 0, the analyzer. So that sets the detector to 0. And copy time profile to worksheet log. So I always save my final peak profile to the log. It gives you a good reference of a known good peak. You know how things were when you started out. All right, so let's move on to the standards tab. So we have multiple calibration parameters like calibration type. So 99% of the time, this will be normal for the M-7600. The other 2 are more for the M-8000. The quantitation mode, so we have peak height and peak area. The number of calibration standards, those will pop up in the chart to the right. You can add by clicking. You can see it adds a new one to the bottom. Our units, there's a wide variety of units already in the software. But if you feel like you need one that's not there, you can always go to Tools to find units and type in your own. We also have the calibration algorithm, so linear or quadratic are your options there. We also have weighted fit and force through blank. And we have a few other QC options in the bottom left. So for our standard concentrations, they're listed here in the chart to the right. You can right click to edit the names if you need to. For the tube or the cup position, you can either type in the box or you can click the ellipses. It doesn't have to be in the standards rack either. You can put it in a regular rack, like 1-1, and the software is not going to work at you. You can also select it from the diagram by clicking the ellipses like that. And in the concentrations, you just type those in the last column. There's also an option to pause analysis after first calibration pending confirmation. I always like that option because you won't waste any samples if the calibration didn't go as expected for some reason. And in the final tab, we have QC test. So this is where you'll enter your concentrations and limits for ongoing quality control testing, like initial calibration verifications, lab control samples, things like that. There's a wide variety of blanks included. You can also input your detection limit. But today we're going to focus on the instrument parameters found under the conditions tab. So this is a side-by-side comparison of the method parameters for the peak profiles that I'm about to go over. For the normal range in the blue chart, I did a file new from the M-7600 normal range template that's built right into the software. So those templates provide a really solid starting point for developing methods using a standard tubing harness. And I'll demonstrate that on the next slide. And the green chemistry method is something that I developed myself. I wanted to create a super fast method for the most commonly used range on the M-7600, which I consider the middle range, the PPB range. So speed, throughput, productivity, that was my focus here. To shorten that analysis, I changed 3 variables that affect the residence time in the system. So the sample uptake time was shortened, so there's less sample going in, while the gas flow and the pump speed were increased. So this was to push the sample through quickly. So this makes less sample travel faster through the system. And there are two big differences between these methods, time and the quantitation mode. So the normal range method takes about 145 seconds, about 2.5 minutes per sample, and the green method takes 70 seconds, so just over a minute. The normal range uses average peak height, while the green method uses peak area. So for peak height modes, you want a nice flat plateau where you can take your measurement at the tallest part of the peak. But for peak area, you can have a tall, sharp peak, almost like a chromatography peak. So let's take a look at what that looks like in practice. So we'll go into our method editor, and we're going to run our highest calibration standard as a peak profile. So first we'll zero the detector, and then we're going to run a single sample. So I'll pick it from my diagram here. It's in the second position of the standards rack. So for the first 45 seconds, the probe is going to move to the sample tube that we told it to, and it's going to draw up our standard. So I chose a 20 microgram per liter or 20 ppb mercury standard. And then after those 45 seconds are up, the probe will return to the rinse station, and then it will draw up rinse for another 100 seconds. So as I mentioned before, this is from a template, so the baseline and the integration time will need to be adjusted to meet our needs. So you can see the baseline is going to be in the middle of the peak right now. So we're going to have to adjust that to a flat part before the peak starts to rise. And for the integration time, it should be across the flattest part of the plateau. So not too close to what I call the shoulder or the front side of the peak, and not too close to the dip from the air slug moving through the gas liquid separator. Which is totally normal, by the way. This dip that's about to happen, right about here, yep, there it goes, is totally expected, because when the probe moves from the sample vial back to the rinse station, it's going to pull up ambient air into the system, and air is primarily made of nitrogen, which suppresses the signal. And then that slight rise after the dip is also okay. This happens because there's a thin film coating the GLS center post, and when the air breaks that thin film, it allows the argon carrier gas to sweep any mercury on the edge center post into the system. So it'll continue to rinse as normal for the remainder of that 100-second rinse time. Coming back down to baseline. And once it finishes up, we're going to adjust our baseline and our integration. About 10 seconds left. All right. So now that it's finished, let's go ahead and go to our Analyzer tab and look at our baseline correction. So we'll zoom in here. We're going to adjust it. The default 40 to 44 seconds. So let's make it, let's say 10 or 15. Let's start at 15. So it looks pretty good. We want it to be away from the rise, so let's scoot it a little farther. Do 10 and 15 for our baseline. I think that looks pretty good. So for our integration, let's zoom in on the top of the peak. And then I'm just going to eyeball it here. I'm going to start with 55 seconds. And then I'll look at the RSD reading at the bottom middle of the chart and see if I'm in the best spot. So we want a low RSD. So 56 looks pretty good. And we're right between the shoulder and that dip and rise. So I think that looks pretty good. So now that we're happy with our new method, let's save it to the log. So this keeps a record of the lamp current, the peak shape, the timing, when the chart was saved. So it's a great reference to have, especially for troubleshooting, because you know what things look like when they were good when you first started. So down here, click the ellipses, and you can see it full screen. All right, so that was our peak profile using our standard tubing and a 20 ppb. So let's run that same concentration with the green chemistry method. So again, we'll open our method editor. We're going to zero the detector. And we'll choose our sample vial. So remember, for this method, our sample uptake is only going to be 7 seconds, and our rinse time is going to be 63 seconds for a total of 70 seconds of analysis time. So by now, our probe is already on its way back to the rinse station. The shape of this peak, you will notice, is different compared to the last profile. So since this is a peak area method instead of peak height, these are going to look more like a chromatography peak with a little bit of a tail, basically straight up, basically straight down, and then it'll rinse for the remainder of the 63 seconds. So take note of where the green and the red integration lines are. So the software is going to look at all of the data between those lines and compute the peak area. So coming back down to baseline. About 10 more seconds left. All right, so let's check on our baseline and beginning integration point, nice and flat. Again, you want to make sure the entire peak is being integrated. So the green line means it will be before the peak rise. So 18 looks pretty good. Again, you can move using the arrows or by typing in. So you can make it 16 if you want to be more conservative. 26 would be a bad choice because you would miss that beginning of the peak. So let's take it back to 18. All right. So let's zoom in on the tail end of the peak. We can see it's still coming down to baseline, but I'm not too worried about that for two reasons. One, this will continue to fall at the beginning of the next peak, so it'll be back to baseline before the next sample, so carryover will be minimal. And two, subtracting like 600 units from a peak area of 6.6 million is insignificant. So it looks really good. So this was what a 20 microgram per liter part per billion peak profile looks like, using the green chemistry method optimized for speed and waste reduction. So let's take a look at results that I got using this method to analyze wastewater samples using US EPA 245.1. So now that I developed my super fast method, I wanted to apply it to a method commonly used by our customers, and I chose US EPA method 245.1 revision 3. So on the left side, we have a brief outline of the procedure that I used. So because the sample uptake is so low with the green pump tubing, it's only about 1.1 milliliters. I ratioed the prep volumes down as written in 245.1 by about 95%. I only used 70 milliliters of sample per tube. I also added in a 20 microgram per liter standard to the curve for 7 standards total. And for all the data that I collected for this, I used blank subtraction and force through 0. And this method could easily be adapted for US EPA 7470A, since they are very, very similar. One important difference between 245.1 and 7470 is the digestion of the standards along with the samples. So in 245.1, the standards are not heated, they're only chemically digested. So my first step was to run an MDL study using 245.1 sample preparation and the green chemistry parameters that I'd optimized. So the calibration curve looks great. You can see the peak profiles at the bottom right. So for my study, I used 7 replicates each of a 0.05 microgram per liter and a 0.1 microgram per liter sample. You can see the raw data on the left, and my final MDL result was 0.021 micrograms per liter, or about 21 part per trillion. Once my MDL was established, I analyzed the wastewater certified reference material. I chose ERM CA-713, which has a certified value of 1.84 plus or minus 0.11 micrograms per liter. So my average result was 1.96 plus or minus 0.011 micrograms per liter, or about 106.3% recovery. My calibration curve R-squared was 497, which is awesome, with an RSE below 2%. And my ICV and my CCVs were at 107% and 106%. So everything's looking really good in control. So it's also notable that only 1.18 milliliters of sample and 3.2 milliliters of stannous chloride were needed for each analysis. So this method was optimized for throughput and productivity, with a total analysis time of 70 seconds per sample. So at this rate, 51 samples could be analyzed in an hour, and that increases the throughput by more than 50% compared to the normal range method that we saw the peak profile for previously. So when comparing the green chemistry to the standard methods and tubing setup, stannous chloride reagent consumption is reduced by 53%, and sample and rinse by 33%. Our waste generation is also decreased by about 40%. For this analysis, the samples generated less than 15 milliliters of waste per sample, or about 760 milliliters of waste per hour. So I'll ask, what's limiting throughput in your lab? Is there not enough time in the day for your analysts to work? Is there not enough autosampler capacity to run all the samples you have? Or is it maybe the amount of chemicals needed for the entire run? So we can address all of those limitations with automation and the green chemistry tubing configuration. So with maximum throughput in mind, we need to look at sample automation. So we will have 3 autosamplers available to pair with the M-7600 through our sister company, Teledyne CTAC. So in the top right, we have the ASX-280. In the middle, we have the ASX-560. And in the bottom, we have our upcoming instrument, the XLR-860. So if we wanted to run our analysis using 8 milliliter sample vials, then we would use a 90 position sample rack. If I use the ASX-860, it can hold 2 racks, so it would have 180 tube capacity. The 560 could hold 360 tubes, and the XLR-860 could hold up to 728 milliliter tubes. So to tie things back to that 245.1 method, if we use the medium-sized autosampler, the 560, at a rate of 51 tubes per hour, we could run for 7 full hours without the need for analyst intervention. So here's a summary of some key capabilities of the green tubing, as well as some application and technical notes that we have written also using the green chemistry tubing. So we went over the sample and stannous flow rates already, 10 milliliters per minute and 2.7 milliliters per minute. Also the 40% reduction in waste at 12.7 milliliters per minute. The sample uptake is variable within the software. The lowest you can go is 5 seconds, which would be about 0.83 milliliters. The instrument detection limit is less than 1.0 nanograms per liter. The typical usable range is 1 to 700. Our short-term precision and long-term precision at 3 different concentrations is comparable to the standard ID tubing. Our throughput is less than 60 seconds. And the average response at different flow rates are listed at the bottom. It's about 60 to 80% reduction. About 60 to 80% of the standard tubing, about a 20% reduction. So what are your next steps? So you can request the green chemistry method template from me. You can submit that within the webinar. You could also email me directly if you'd like. And I highly encourage you to buy the green chemistry tubing. If you're domestic in the United States, you can order on our web store or from your local distributor, or however you typically order consumable parts. So here's a quick reminder of the part numbers on the right side of the screen. We have the white tubing, which would be the drain and the sample, which is 15-4308-102, and the orange-yellow stannous chloride reagent tubing, which is 15-4309-102. So that concludes my presentation for today. Thank you for listening. Please feel free to reach out if you have any questions. My phone number and email are listed here. QR codes to our social media is at the bottom of the slide. We will send out a link to the presentation in a few days if you'd like to view it again. And thank you for taking the time to learn about our mercury analyzers today.